A binary search tree (BST) is a special kind of binary tree that stores keys or values in a way that makes searching fast. Formally, a BST is a tuple T equals V, E, key where V is the set of nodes, E is the set of edges, and each node V and V carries a key of V. The BST invariant must hold for every node V. All keys in the left subtree of V are less than key of V. All keys in the right subtree of V are greater than key of V. If duplicates are allowed, a common rule is to put equal keys either always to the left or always to the right, or to store a counter. Because each node has at most 2 children, the structure is a binary tree. The height h of the tree is the length of the longest root to leaf path, with the root at depth 0. The invariant guarantees that an in-order traversal of the tree yields the keys in sorted order, just like a phone book that you can look up by repeatedly having the remaining pages. This ordering property enables logarithmic time search when the tree is balanced. Key structural properties. Binary property, each node has 0, 1, or 2 children. Ordering property, left keys less than node key less than right keys, applied recursively to every subtree. Uniqueness optional, many textbooks assume all keys are distinct. If not, a tie-breaking rule is part of the definition. Height versus size. For n nodes, h is less than or equal to n-1. When the tree is perfectly balanced, h equals the floor of log base 2 of n, the height directly determines the cost of basic operations. These simple rules together give the BST its power. The work to find, insert, or delete a key is proportional to the number of edges we must walk, that is, the height h. Explanation: the recursive search algorithm follows the BST invariant step by step. A procedure. 1. Start at the root node Rs. 2. If R is null, the key is not present, return not found. 3. Compare the target k with R.key. If k equals R.key success, return the node or its value. If k is less than R.key, recursively search the left child R.left. If k is greater than R.key, recursively search the right child R.right. 4. The recursion ends when a leaf's child is null or when the key is found. Pseudocode. Define search with parameters node, k:. If node is none, return none, not found. If k equals node.key: return node, found. Else if k is less than node.key: return search left parenthesis node.left, k right parenthesis. Else return search left parenthesis node.right, k right parenthesis. Time complexity derivation. Each recursive call reduces the remaining height by exactly 1 because we move from a node to one of its children. Let t of h be the worst case time when the current subtree has height h. The work done in a call is a constant c, compare and a few pointer accesses plus the work of the next call. T of h equals t of h minus 1 plus c. T of 0 equals c. Solving this linear recurrence gives t of h equals c times h equals big O of h since h is less than or equal to n-1. The worst case is big O of n, but for a balanced BST, h equals theta of log n, yielding big O of log n. Intuitive analogy - imagine a library where each shelf is split into a left half, books with titles alphabetically before a pivot, and a right half after the pivot. Searching for a title means looking at the pivot book, then walking to the appropriate half and repeating. Each step halves the search space, which is why the number of steps grows with the height of the tree. The iterative version replaces the call stack with an explicit loop, which is often preferred in production code, because it avoids the overhead of function calls and the risk of stack overflow on very deep trees. Define iterative search with parameters root and k set cur to root. While cur is not none, if k equals cur.key, then return cur. Else if k is less than cur.key, then set cur to cur.left. Else set cur to cur.right. After the loop, return none. Set a pointer cur to the root. While cur is not null, compare k with cur.key. If equal, return the node. If k is smaller, move cur to cur.left. If larger, move cur to cur.right. If the loop ends, we have reached a leaf's missing child, meaning the key does not exist. Comparison with the recursive version. Call stack recursive search uses system call stack with depth equal to height. Iterative search uses no extra stack, only a few local variables. Memory overhead recursive search uses O of h extra space for stack frames. Iterative search uses O of one extra space. Readability, recursive search is often clearer, mirroring the definition of a binary search tree. Iterative search is slightly more verbose but still simple. Tail recursion optimization. Some languages such as Scala can eliminate the stack, but many C-like languages cannot. Iterative search always has constant space. Risk of overflow. Recursive search may overflow for very unbalanced trees where height is approximately, and iterative search has no risk. Both algorithms perform the same number of key comparisons, so their time complexity remains O of H. The choice is usually a trade-off between code elegance with recursive and guaranteed low memory usage with iterative. Explanation::insertion is similar to search, but when the recursion reaches a null child, we create a new node there. The algorithm respects the BST invariant, so after insertion, the tree remains correctly ordered. Def insert left parenthesis node comma k right parenthesis colon. If node is none colon return node left parenthesis k right parenthesis hash base case place new node here if k equal node dot key colon hash handling duplicates option 1 ignore option 2 node dot count plus equals 1 if we store a frequency return node hash no structural change elif k less than node dot key colon node dot left equals insert left parenthesis node dot left comma k right parenthesis else colon node dot right equals insert left parenthesis node dot right comma k right parenthesis return node hash return unchanged or updated subtree root. Handling duplicates dash store an integer count in each node. On equality increment the count. Ignore duplicates dash simply return the existing node unchanged as above. Force placement dash consistently send duplicates to either the left or the right subtree. This still satisfies the invariant if the rule is uniform. Complexity analysis. The recursion follows a single path from the root to a leaf just like search. Let t sub ins of h be the time for a subtree of height h colon. T sub ins of h equals t sub ins of h minus 1 plus c. Where c is the constant work of a comparison and a pointer assignment. Solving gives t ins of h equals O of h. If the tree stays balanced, h equals theta of log n and insertion is O of log n in the worst case of a degenerate sorted insertion order. H equals n minus 1 and the cost becomes O of n. Real-world analogy dash think of inserting a new word into a dictionary that is kept alphabetically ordered. You scan the pages until you find the spot where the new word belongs, then you slip a new page in. The number of pages you flip corresponds to the tree height. The recursive version is concise and directly mirrors the logical definition of a BST, making it a common teaching tool. The iterative insertion algorithm walks down the tree to find the correct null child position, keeping track of the parent node, so that it can attach the new node. The step-by-step procedure. Create the new node as node of k, but hold off on linking it. If root is null, set root to new node, and finish this handles the empty tree case. Initialize two pointers cur as root and parent as null. Loop while cur is not null, set parent to cur. If k equals cur key handle duplicate ignore or increment count, and return the unchanged tree. If k less than cur key set cur to cur left else, if k greater than cur key set cur to cur right. When the loop terminates cur is null and parent points to the leaf where the new node belongs. Attach the new node if k less than parent key set parent left to new node, else set parent right to new node. Return the unchanged root of the tree. Pseudocode. Define function iterative insert taking root and key. Create new node as node of key. If root is none, return new node. Set current to root and parent to none. While current is not none, set parent to current. If key equals current key, return root. Else if key less than current key, move current to current left. Else move current to current right. After the loop, if key less than parent key, set parent left to new node, else set parent right to new node. Return root. Correctness proof loop invariant. Invariant. At the start of each loop iteration, parent is the node that would be the parent of current if current were the spot for insertion, and the subtree rooted at current is the region where the key k must belong according to the binary search tree invariant. Initialization. Before the first iteration, current is root and parent is null. The invariant holds trivially because the whole tree is the candidate region. Maintenance. The comparison decides whether the key belongs to the left or right subtree of current. The algorithm moves current to that child and sets parent to the old current. Because the binary search tree ordering is preserved, the key cannot be elsewhere, so the invariant remains true. Termination, the loop stops when current becomes null. By the invariant parent is exactly the node whose left or right child is empty and into which the key must be inserted. The final step attaches new node as that child, preserving the ordering property. Since each iteration reduces the height by 1, the algorithm runs in big O of h time and uses only big O of 1 extra space. Analogy: imagine walking down a hallway of branching doors, always choosing the left door if your destination name is alphabetically earlier. Otherwise, the right door, you keep a mental note of the last door you passed parent. When you reach a dead-end null, you open a new door there and place the item. This iterative style is what you will see in most interview coding solutions because it avoids recursion depth limits. Explanation: the height of a BST is the key factor that decides how fast operations run. When we build a tree by inserting keys one after another, the shape of the final tree depends on the order of insertion. Worst case height big O of n if the keys arrive in sorted order, either strictly increasing or decreasing, and we always attach duplicates to the same side. Each new key becomes the right or left child of the previous node. The tree degenerates into a linked list, 1 to 2 to 3 to n. The height h equals n-1. The recurrence that describes this construction is h sub n equals h sub n-1 plus 1, with h sub 1 equals 0. Solving gives h sub n equals n-1, which is big O of n. Thus, any search, insertion, or deletion may require scanning all n nodes. Average case height theta of log n. Assume the keys are inserted in a random permutation of the n distinct values. The expected shape of the tree is much more balanced. Let h of n denote the expected height of a BST built from n random insertions. A classic recurrence is h of n equals 1 plus 1 over n times the sum from I equals 1 to n of the maximum of h of I minus 1 and h of n minus I, with h of 0 equals h of 1 equals 0. The term I corresponds to the rank of the first inserted key, the root. The left subtree receives I minus 1 keys, the right subtree receives n minus I keys. The height of the whole tree is 1 for the root plus the larger of the two subtree heights. Solving this recurrence asymptotically yields h of n equals theta of log n. More precise analysis shows the constant factor is about 4.311 for binary search trees built from random insertions, i.e., h of n is approximately 4.311 log base 2n. Intuition via divide and conquer. When the root splits the remaining keys roughly in half, which happens with probability about 1/2 for each insertion, each recursive subtree contains about n over 2 keys. After log base 2 and such halvings, we reach a subtree of size 1, giving a height proportional to log n. Summary table. Columns are insertion order, expected height h, big O of height and reason. Row 1, sorted or reverse sorted, n-1, big O of n, tree becomes a chain. Row 2, random permutation, theta of log n, balanced on average due to random splits. Row 3, adversarial but not sorted, for example always inserting the median, theta of log n, constructed to stay balanced. Understanding this height analysis is crucial for exam questions that ask you to argue why BST operations are big O of h, and to give the best and worst case bounds in terms of n. Explanation: when you are asked about edge cases. In an exam, the grader wants to see that you understand how the algorithm behaves in the corner situations that can break a naive implementation. 1. Empty tree, search dash the root pointer is null, the algorithm immediately returns not found or null. Insert dash create a new node and set the root reference to it. This is the only place where the root changes. 2. Leaf insertion. A leaf is a node whose left and right children are both null. Inserting a new key that belongs under a leaf follows the same steps as any insertion. Walk down until you encounter a null child, then attach the new node there. No rotations or rebalancing are needed for a plain BST. 3. Duplicate keys. Different textbooks choose different policies. Ignore dash do nothing, the tree stays unchanged. This keeps the set of keys unique. Count dash store an integer count in each node on duplicate increment count. Search returns the node and its count. Force placement dash always go to the left or right subtree for key equals node.key. The invariant still holds because the rule is consistent. When writing pseudo-code, explicitly comment which policy you are using. Exam markers look for that clarity. 4. Rebalancing considerations. A plain BST can become tall big O of n. Self-balancing trees, a VL, red, black, tree, etc. perform rotations after insertion to keep the height bounded by big O of log n. When to rebalance (dash) after an insertion, walk back up the path to the root checking a balance condition. For example, height difference less than or equal to 1 for a VL. If violated, apply a single or double rotation. Impact on exam dash. If the question mentions BST, only you may ignore balancing. If it says a VL tree or maintain O of log n height, you must discuss rotations. 5. Practical checklist for an exam answer. 1. State the precondition tree satisfies BST invariant. 2. Describe the base case null pointer for both search and insert. 3. Show how you treat duplicates. 4. Mention what happens when the tree is empty. 5. If asked, outline the extra steps for rebalancing rotations and give a tiny example. Having a clear bullet point list like the one above helps you earn partial credit even if you run out of time to write full code. Real-world analogy. Think of a phone directory that starts empty. Adding the first contact creates the book root. Adding a new contact with a name that comes before all existing names puts the entry at the very beginning leftmost leaf. Adding a duplicate name could either be ignored, you already have that person, or you could note 2 entries next to the name. If you keep adding names in alphabetical order, the directory becomes a long scroll worst case. To avoid a scroll, you periodically fold the paper and insert a new index page rotation, so you can still find a name quickly. A. Tracing a search operation. Question: given the BST built from the case sequence 50, 30, 70, 20, 40, 60, 80, trace the steps of searching for the case 60. Show the visited nodes in order. Answer: 1. Start at root 50, compare 60 greater than 50, go right. 2. Visit node 70, compare 60 less than 70, go left. 3. Visit node 60, equal found. Visited order: 50 arrow 70 arrow 60. Explain that only 3 comparisons were needed because the height of this tree is 2, root at depth 0, leaf at depth 2, thus O of H with H equals 2. B. Constructing a BST from a sequence. Question: insert the keys 15, 10, 28, 12, 17, 25 into an empty BST, ignore duplicates. Draw the final tree or list parent-child relationships. Answer step by step. 1. 15 becomes the root. 2. 10 less than 15, left child of 15. 3. 20 greater than 15, right child of 15. 4. 8 less than 15 and less than 10, left child of 10. 5. 12 less than 15 and greater than 10, right child of 10. 6. 17 greater than 15 and less than 20, left child of 20. 7. 25 greater than 15 and greater than 20, right child of 20. Resulting relationships. Diagram: 15 at the root, left child 10, right child 20. 10 has left child 8 and right child 12. 20 has left child 17 and right child 25. The height is 2, so any subsequent search or insertion will cost at most 3 comparisons. See proving the O of H bound for search insert. Question: prove that searching for a key in a BST with height H takes at most C times H plus D time for some constants C and D. Answer: inductive proof outlined. Base case: if H equals 0, tree has a single node or is empty, the algorithm performs one comparison and possibly returns, which is bounded by C times 0 plus D for suitable C and D. Inductive step: assume any BST of height less than H satisfies the bound. For a tree of height H, the algorithm does a constant amount of work C1, compare the key with the root, and then recursively proceeds to either the left or right subtree, whose height is at most H-1. By the induction hypothesis, the recursive call costs at most C times open parent H-1 close parent plus D total time. T of H is less than or equal to C1 plus C times open parent H-1 close parent plus D, equals C times H plus open parent D plus C1 minus C close parent. Choosing C greater than or equal to C1 and adjusting D gives the desired bound. Hence, the worst case cost is linear in the height, i.e. O of H. Edge case awareness: mention what happens if the key is absent. The algorithm reaches a null leaf after H comparisons. What exam graders look for? Correct traversal: list every node visited, not just the final answer. Clear construction: show where each new key is placed. A diagram helps. Formal reasoning: a short induction or recurrence argument with constants, shows mastery of the O of H claim. Edge case awareness: mention what happens if the key is absent. The algorithm reaches a null leaf after H comparisons. Practicing these 3 types of problems will prepare you for most BST questions. that appear in data structures courses and technical interviews. Tip: when writing your answer, keep the explanation aligned with the index of the subtopic. Search, insert, height, edge cases, exam style. This makes the grading rubric easy to follow.